Again, welcome. Today, I'm hoping to be the last day, basically, where we deal with chapter 22, which is the second chapter of this book. And we're going to get going with chapter 23. And chapter 23 deals with the electrical potential. So I promise that we still have some applications. Here is the deal. I'm going to do one of the problems now, do chapter 23 in the lecture. And then because we are still not ready for the lab, later on during lab time, we can meet and do more problems from this one and maybe discuss stuff. And because chapter 23, I'm really kind of divided onto how many problems. I think I'm looking at 3 to 4 minimum, potentially more problems that we can do. And you will see my reasoning why chapter 23 needs more applications in it, okay? Which is the electrical potential, okay? So that's basically where we stand on things, okay? So let me first of all get my share the screen. Do you guys have any questions before I do that? Where is my, here it is, chapter 22. What happened? Okay. Are you going, did you guys see the OneNote, or did I share with you something else?
We saw your mastering page.
So why? Oh man, sorry. Okay, one message that was sent by one of you guys about mastering physics is that you guys wanted the date to change on chapter 22 because we really did not finish it. So, and she was right, and I think I promised that anyway. So I made the change on the date, okay? So here is what I want. Am I on the right page now?
Yeah, you're good now.
Okay, very good. Okay, guys, I changed the date on the assignment, okay? And I shifted them all because it looks like we're going slower than what I was planning initially, which is fine. I mean, it's not a complaint or anything like that, but so that you guys know, okay? Okay, so we did problem, I think we did this problem to death. And I was hoping that you guys would finish the, try at least to start the other two examples, the other two problems similar to it. And chances are, if it's not in this exam, it's going to be in the second exam because there will be some stuff similar to these things also when we do magnetic fields. Because in magnetism, you will see the current densities that's similar to the charge density in here. And instead of creating electric fields, they will create magnetic fields. So that's basically the parallels with that, okay? Okay, so we decided to do problem 53. So let me tell you why this is a very good problem that's not going to require a lot of things to do. Problem 53, again, it should be in every textbook, okay? Doesn't matter which edition you have, it should have it. So here is an insulating sphere with radius A has a uniform charge distribution rho. The sphere is not centered at the origin, but at R equals to B. So basically the first part is set up for the problem, really. So you have a sphere in here, and it's located at a vector B from the origin somewhere. So this is its center, and this vector is B, and this is the axis. Of course, I'm drawing them in the XY plane, but of course we can draw this. This is a sphere. It needs the coordinates in space. So think of this one as there is a Z component that is coming out of the screen, and this B is some vector in space. So it's not necessarily that it is a on the plane XY. Okay, so this is a sphere, not a circle. Okay, and so this distance from it is B from the origin somewhere. Remember the lecture, we found the electric field for a solid sphere inside the sphere, okay? We're not talking about outside the sphere. Inside the sphere was given by this proportionality to R. And I'm trying to go through these notes in here to see what it is. One of you guys, I don't know if it's in your class or not, they asked for these notes. And I thought it's not a good idea to share with you these notes because first of all, they're scribbled all over the place. And second, because I really want you guys to go through these same exercises, because as I'm making the argument, Sometimes I go back and scratch things and change things and multiply by a factor of 2 or something. So at the end, you will end up with something that doesn't make sense because it's missing several steps. So that's one thing. The other thing also, I really want you guys to go through the rationale and the reasoning, okay? Far more important than teaching physics, in my opinion, or learning physics in this class is learning how physicists think and learn that process. Because at the end, if you're wondering what in the world is the electric field inside a sphere, I know I took it a long time ago when the charge distribution is uniform, but I don't remember. Is it a 3 in the denominator, or is it a 6, or is it 4 pi epsilon naught or something? You can just Google it and you will find the answer. Or open the textbook and you will find the answer. But how do you think solving a problem? How do you think as a physicist trying to work your way through it? That is a skill that you need to learn. You cannot Google that. That is a skill that you need to have it developed in your mind. And this is true for all my classes, by the way, whichever class I'm teaching, for A, for B, for C, even the non-calculus based classes that I teach, and I teach a couple this semester. One of them is general physics. I emphasize on this idea too, and how to basically make the case for arguments and how to basically come up with things, okay, physical science. So in other words, this is really what I cherish the most, and that's what I'm hoping that you guys will develop. So sharing the notes is not going to be very helpful in this process. As a matter of fact, I think it's not good. Going back through the steps yourself, writing it yourself, pulling your sleeves and getting sweating through it and understanding every single step, that is the key. And that is the only way, okay? So it's not really a spectator sport, so you really have to do these things. That's why I'm asking you, when the class is over, when you do these problems, you go through them and try to understand them, see that every step makes sense to you, and that the result makes sense to you, and that how can you make that problem somewhere else and try to apply it somewhere else so that you develop that skill. Does this make sense to everybody? Yes? Okay, very good. So here is a result that we found last time. The electric field inside the sphere, where this R was actually from the center of the sphere. So if we go back in here, and if somebody asks me in this problem, what is the electric field in this point in here? Doesn't matter, this point in here. So let me draw with a different color. This point in space. So this is clearly inside sphere. So what I really care for is this distance, which I'm going to call R prime. Okay, and this vector. So the electric field inside is given by that same expression. E is equal to 1/3, 1/3 epsilon naught times the charge distribution, which is rho in this case, times R prime. So that is the answer to that question. I mean, if somebody wants the electric field, not this R, or not this R, as a matter of fact, there is another R in here that you have to be careful with, this vector R. This is the vector position of that point where you're trying to find the electric field. This is normally the vector R. It points to where the position is. So the vector R and the vector R prime are not the same, because R prime is measured only from the origin. So when we measured this expression in here earlier, and we used Gauss's law, a sphere around the center in here, and we used the symmetry left and right until we got the answer, this is what we got. So what matters in here, this vector is not any vector. It has to be originating immediately from the center of the sphere and inside the sphere somewhere. So that is the electric field in there. Okay, so that is what this problem is saying. I mean, it's so when they shift the origin now, we have to be careful. It's not in the center of the sphere anymore. It's somewhere else. Okay. Now the sphere is not centered at the origin, but at a vector B. Show that the electric field inside the sphere is given by this expression. Okay. You can clearly see from this geometry, I'm going to blow it up so that you can clearly see it better. The vector B is from the origin to the center of the sphere. The vector R prime is from the center of the sphere to a point in space. The vector R, which is that point in space where we are interested in measuring the electric field. So it's clear from this geometry that the vector R is equal to the sum of the vectors B and R prime. And all we have to do is plug this R prime into there, which is just the difference of R minus B, and we have found the answer. The electric field then is rho over 3 epsilon naught times the difference between the vector R and B. Does this make sense? It's a one-step problem. One-step question.
Is this from the 15th edition?
Yes, problem 53 from the 15th edition. You're interested? You have the 14th instead?
Yeah, I have the 14th edition. I
Fine.
think it's 57, but I just want to confirm.
Is it 57? If it is 57, it might be 57. Okay. Where is my 14th edition now? Oh man, did they dispose of it somewhere? Okay, if you can't find it, please let me know. I will find it somewhere. And I don't see it in here. Hold on. Okay, let me, because that's a good question. Usually I'm assuming that you guys are following, and that's not good if you guys are not. Okay, when is the 14th edition? Okay, guys, I didn't find my 14th edition, but it's somewhere in here. I will find it, and I will tell you exactly which problem that is. And Martin, remind me again about these problems, okay?
All right, thank you.
Okay, good. I found it. It was under a pile of other books. It was under Feynman books. Okay. So, 14th edition, chapter 22. Chapter 20. Yes, it's exactly problem 57. Okay. And the previous problem that we did last time was problem 56, but away from this problem, from this edition. And yes, it looks like problem the 15th edition has a little bit more problems in this chapter than the others. Okay, not that much. Okay. Problem 58 is similar to problem 54 in this edition. Okay. I think, is everybody good now? Following still?
Yes.
Okay. So this is the answer to the first question. It's very, very simple geometry in this case. All we have to do is just find R prime in terms of B and R. That's all. And we plug it back into the expression that we found last time, and we're in business. So this doesn't require a lot of really, and if you want to, you could do another Gaussian argument in here and all of that. You're going to arrive to the same result we arrived to last time. And this is basically the result for that part. That's part A. That's not really the problem. That's not the trick of the problem. Part B. An insulating sphere of radius R, this is a different problem, okay? This is not the same sphere as before. This is another one, okay? They're talking about another one. Of the radius R has a spherical hole of radius A located within its volume centered at a point B from the center of the sphere, okay? So that A is less than B is less than big R, okay? And cross section of the sphere is shown. So basically this is what they have done. You have a big sphere of radius R. They came in the middle in here, it's a distance B, and they took a hole in it. They made a hole in it, another sphere, if you wish, that has nothing in it. So this distance is B, and the radius in here is A, and they tell you specifically A is less than B is less than R, okay? So that's basically the geometry we're looking for. This sphere now has a charge distribution rho. And the inside has nothing. It's a hole. There is nothing in it. So this is an empty. It's not like it doesn't have a charge or anything. It has nothing in it. It's just like basically somebody came and chewed out of it, chunk, which is like a sphere, an apple, basically. The solid sphere of the sphere has a uniform charge distribution rho. Find the magnetic field E inside the entire hole. Okay, what is E here? That is the question. No matter which point you take in here, and if you're tempted to use Gauss's law, you're in big trouble because you don't have symmetry. So if I want to use a Gaussian surface in here, there is no spherical symmetry. It's clearly there is a missing chunk of that sphere, the Gaussian sphere. If I want to use the integration also, I have a big problem also. If I take a volume in here and use chapter 21 and find the electric field somewhere in here, and then sum up, the boundaries in here of integration will make up this problem very hard. So in either case, it's very, very difficult to do the problem. But here is the trick. Instead of solving this problem, we're going to ignore this problem and solve a different problem altogether. And here is a problem that we're going to solve. What we're going to do in here, we're going to take this entire sphere of radius big R and sprinkle it with a charge rho. So take the entire sphere now and have in it rho, okay? And bring another sphere of radius, so this radius is R, by the way. And this charge now has bring it with a distribution negative rho. So if this charge was positive, bring one that is negative. If this charge was negative, bring one that is positive, that's all. And take now, this radius in here better be A. Okay? And take this one, the center of this one, and place it exactly here at the point B from the center. So now if I place that sphere in here, there will be plus rho minus rho. So I have no charge in here. Do you guys see that? So if I bring this similar one to it, then they will cancel. Correct? Yes or no? So if I pair the charges in here, the positive charges, that's one in the chart. This has a positive charges everywhere. It doesn't matter. Okay, so it has everywhere, including these two charges, for example. And this has exactly what needs to be done to cancel those two charges. Has this charge and has this charge because it has the same distribution per unit volume. So this has this much per unit volume, and per this volume, it has two of them. Per that volume, this also must have two of them because it's the same volume. So if I match this in here, this positive and negative will cancel, and this positive and negative will cancel, and it will have no charge at the end. And this is similar, not exactly similar, to this problem, because this problem has charge everywhere, like this one has charge everywhere, rho, distribution per unit volume, and has no charge distribution inside. This one also has the same charge distribution everywhere and has no charge distribution inside. Does this make sense, at least, that these two are equivalent? Okay, so empowered by that, let's do things. Let's find now, using our BFF. So what is that? We're going to use what now? Who is our BFF in this class?
The superposition principle?
You guys agree? Superposition principle. Basically, this is what we're going to do. We're going to go to a point inside that sphere. Let me redraw it, okay, because it's a mess now. Let me take the big sphere now of radius r and go distance b, and somewhere within A, I'm going to find the electric field in there. Obviously, it's going to go like this, okay? So this is the electric field. So we're going to find the electric field due to the positive distribution of charges rho, or due to rho, okay? And that's one thing. So we're going to find the electric field from the big sphere, okay? We're going to call it big R or something, big R, okay? Then we're going to take the little sphere of radius A and go to the same point. By the way, these are supposed to be on top of each other. I know I separated them just to do the mathematics, but they're supposed to be living on one another, okay? So I just separated them. So this point in here, which I'm going to call point P, is the same point P in here. The only reason I separated them in here is just to do the math. So if I find now the electric field coming from this charge distribution from the A of radius A, the E of radius A, then I'm in business. So I have an E to the from the big R, which is going to be a vector, by the way, and the E from the little circle. I'm going to say that that's exactly E by superposition. Basically, calculate one, calculate the other, and just add them up and say that this is the actual electric field in that point. So this is the electric field in here. If I measure the distance from the origin and call this one R, and this distance, of course, is the vector B, and this distance is, of course, of R prime, okay? So it looks like the electric field now, due to R only, using that same formula, is sigma over 3 epsilon naught times R, because I'm choosing the origin to be exactly this point. Whereas the electric field due to A, it has a negative rho charge distribution. So it's not rho anymore, it's minus rho now, divided by 3 epsilon naught. And the vector that I'm going to do in there is R prime, okay? And now by superposition, I just need to add these two vectors, that's all. So E is simply going to be sigma over 3 epsilon naught, which is common to both terms, and it's R minus R prime. Let's look at this R minus R prime business in here to see exactly how it looks like. So this is B, this is R prime, and this is R. So if I take R and subtract from it R prime, that means I add to it the opposite. So I'm getting B. Do you guys see that? In other words, B plus R prime is equal to R. So it's clear from this expression that R minus R prime is B. Yes? From the geometry only. Make sense? Okay. So the electric field then inside the little sphere, anywhere in the sphere, is 3 over epsilon naught. I mean, rho over 3 epsilon naught times A, times B, I'm sorry, where B is the vector from the center of the big sphere to the center of the small sphere, okay? And it's always there. So this is how it looks like. So this is a strange result, okay, in a sense, but it's a powerful result too. That means the electric field is constant everywhere in the sphere, in the small sphere, and it has the same magnitude. And it's the same direction also. It's always pointing in where B is pointing. So if B is pointing this way, this electric field is pointing in that direction. So if I take my sphere and rotate the whole thing with the hole inside, then it rotated also in the same direction, the electric field inside that hole will stay constant because this B doesn't change. So in other words, E in magnitude is rho over 3 epsilon naught B. So in magnitude, it stays the same as long as the charge distribution is the same. And the direction now follows B, that's all. And this is a very powerful result. All we did was the superposition, though, and basically superposition was true everywhere. So it's not just in here, even in the big formula, it's always there. And all we did was replace the actual problem. This is the real problem, by the way. We have a sphere with a hole in it, okay? A small hole in it. And that hole is actually a sphere too. Okay? And we wanted to find the electric field inside that hole, basically anywhere in the hole, okay? We want to find the value of it. So if there is a problem, we want to test things or something, this is where we're going to go and find that electric field. So if we point them in here and there, we're going to find the same electric field everywhere. So what that means is, what we did actually is, we replaced the actual problem by another problem. By saying, look, what I really have is, I have the actual sphere removed from it. So this is the removed from it, actually added to it in this case. Another similar sphere with the charge distribution negative rho, because negative rho and positive rho, they cancel. And now all I have to do is apply this formula twice, basically. Apply it for the big sphere with the charge distribution rho, and you got this answer. And now apply it with a charge distribution negative rho, which is the same formula, by the way, that we found, except r prime in here. And that's why the purpose of the first question was to get you to understand that it's r prime, not this vector r, okay? Because in the big sphere, we're measuring it from the center of the sphere, whereas from the small sphere, we're measuring it with respect to the center of the sphere itself, okay? So that's why we have to use that r prime in here to make the distinction. And this minus is coming from the fact that these two distribution charges must be canceling one another. They must be one opposite to the other. Once you have that, then you just look at the geometry, that's all, okay? Which is plane geometry. You have from the center of the big sphere of radius r to the center of the sphere of radius a, the distance b. This r prime is less than b than a, by the way. We are still inside that big sphere, okay? Because we are not calculating it toward the edge of the small sphere, where we would put r prime equals to a. No, we're not. We're calculating it inside that small sphere. That's why we put r prime in here. And now the point is still referred to by the vector r, okay? And clearly from this geometry, r is the sum of b plus r prime. In other words, r minus r prime is the vector b itself. And this gives me a result that doesn't depend on anything. So it's the same everywhere inside the sphere. Okay, do you guys understand this method? It's called by subtraction because of its power. At least for this example. Okay, very good. As any other method that you learn in physics or any class for that matter when you're solving problems, it requires practice. It requires you guys to practice, okay? If you don't practice these things, they will not stick, number one, and you're not really sure how to do them, okay? So that's the only thing I can require for you to do. The next problem on both editions is actually identical, with the exception that instead of dealing with spherical symmetry, we're dealing with cylindrical symmetry, and that is it. It uses the same method, okay? So that is it. So I promise you guys we do problem 55 from this chapter, which we are. But we're not going to do it now. I'm going to defer that to 2 o'clock in the afternoon when we meet for the lab, because we are not there yet in terms of the lab, okay? And in terms of the capacitors, which is the next lab. So most likely, we're going to do the lab next week on Wednesday when we meet, because I think we will have the capacitors by then defined, and we should be able to do some experiments then. So instead, we're going to jump into chapter 23, because we should have started that actually, on Monday. But because we're taking our time, which is not a problem, honestly, as I was saying, it's fine. So we are starting it today. Any questions before I do that? Let me tell you about the problems that I'm thinking to do from chapter 23 right now, so that you're thinking ahead. And this is from the 15th edition. Again, they might be different from the 14th edition, at least the numbers there. Problem 41. Okay, that's for sure what we're going to do, okay? Because that has implications immediately on the capacitance. And it's identically problem 61 also, although I was debating whether or not I should do one and you guys do the other or something, but I'm going to do that because the geometries are a little different. One of them is for coaxial cables, like the ones that are used for your TV reception, the ones that come from basically for the cable company to your TV. So, and that is important because it has a lot of applications. The other problem also is for spherical, basically, which really hardly, I don't know, probably it's used in the industry also, spherical capacitors. And then the other problem that I am thinking about, but not 100% sure because of its applications in science, and that is problem 57. Problem 57 has the sodium chloride, basically, atom, basically how the crystalline structure, actually, crystal, and you're supposed to calculate the energies and things like that, okay, which is a nice problem to really do. So at this point, I'm leaving it as an iffy problem, so we may or may not do. The other problem also that is an important problem, and that is the Geiger counter problem, but I'm actually debating that one too, and that is problem 62. You see a lot of applications for the potential issue here, okay? Problem 72, which is actually an interesting problem because it also involves physics 4a applications for mechanics. And that is actually, I'm debating. I think I gave that problem sometime in the past as an exam, okay? Not this past semester. I think it was a long, long time ago when I was doing physics 2, okay? Problem 76 is important, although it's a calculus-based problem, similar to what your calc instructor will give you. But that's something that we're going to do because you need to practice on how to calculate the electric field from the electrical potential. So you need to know how to do that, okay? And when you go to your calc instructor, they might give you a problem with no dimensions or no meaning in terms of physics, but this has meaning, okay? So we're going to do problem 76 for sure. Problem 77 is a data problem, and you know how crazy I am about data, so we're going to do that. Okay, problem 80 is a nice problem, and oh man, there is a lot of problems. Problem 79, actually, about the Millikan experiment and how he determined the charge of the electron. It's also a nice problem, too. Problem 81, which I'm not going to do, but I'm just bringing your attention to it. It has to do with biology, basically, how the flow of blood inside the cells is actually, we use the voltage actually to measure that and check the blood pressure and do all kinds of things on it. And determine clots and things like that. So it has application in biology too. So there are a lot of applications. For sure, what we're going to do are problems 46. No, problem 46 is a simple application that it's a good idea to do. And this is probably what maybe somewhere else in other classes you might do at most. But I want you guys to think about it. So I'm not going to do problem 46. But the problems I'm going to do for sure are problems 61 and problem 41, and the two problems 76 and 77. And depending on time allowance, I probably will touch on 57 and maybe 62 and the other few that I mentioned that I think are exciting problems, okay? So this is basically for chapter 23, okay? So let's start chapter 23, and we started from when we left off way back in chapter, what is it, 6? When we did the energy, when you guys did the energy. You remember that debate that you guys had it for physics 4a? When you introduced the potential energy and the kinetic energy and the work energy theorem and the conservation of mechanical energy versus that of the non-conservative forces, conservative forces. Do you remember that discussion that you guys had a long time ago? When was the last time you guys did physics 4a? Martin at least remember this discussion. Anybody else? Anybody else remembers this? When you did the work energy theorem that basically says that if a force basically does F equals to ma, that is basically your starting point, this is equivalent to saying that the work will do work, and this work is equal to the change in the kinetic energy of a system, and hence this is the work energy theorem. And this one is a theorem. And this one is actually equivalent to F equals to ma. And you take a step further that you find that in calculating the work, there are two types of work. There is conservative work, there is conservative forces that have the work does not depend on the path, but depends on the initial and the final position. And you define a potential energy in there, which is by definition in such a way, basically, that the force is equal to minus du dx. And the total energy, you define it as the kinetic energy plus the potential energy, where this is actually the potential energy. I wrote it as being Q in this case, because we technically write it usually as U. This is the kinetic energy plus U. This is the mechanical energy. In any transformation the system goes through, the change in the total mechanical energy is equal to the work of the non-conservative forces. Does this ring a bell to some of you? from 4A? Yes, okay, at least one person is resonating, actually more. Good. Okay, that makes me feel better now, since there are at least two people. Okay, more than that, very good. So, okay. Okay, so it's really not, if you're not sure 100% about it, first of all, it's probably the biggest topic that you should have had, probably in addition to F equals to MA in physics 4A. So if there is one thing that you probably need to grasp, it's this one. If you are going to major in physics, this is a big deal, okay? If you're going to be an engineer of any kind, this is probably not that big. I mean, it's important if you're going to do probably virtual work and for structural, basically stability and things like that. So that relies on these ideas. So if you're going to do some sort of civil engineering or some stuff like that, so you need to understand these ideas too, okay? But at that point, you rarely deal with frictions. And no, actually you have frictions also, you deal with those things. So, but in terms of conceptual ideas, this is a big deal in here in physics. As a matter of fact, there is a bigger deal that will come toward, I forgot which chapter that is at this point. And we're going to debate it. And you will see me sweating when we're discussing that one, because of the fact that it's a dangerous realm, basically. It's like walking on a tightrope using these principles. And here right now, it's going to be fine because we know exactly how this thing works. But for an inductor down the road, which is clearly a non-conservative force, but somehow we're going to apply something called Kirchhoff's rules to solve the problems when we do it and we get the results correct. And because we come up with an interpretation for those non-conservative forces with their equivalent that are conservative, and basically we we wipe the sweat and we say, okay, it's going to work. Okay, so if you're going to be an electrical engineer or electronics or something, you don't care for that discussion whatsoever, because you just apply Kirchhoff's rules and you're fine. If you're going to be a physicist, you really need to pay attention to the details at that point, because you need to understand what kind of argument you need to make for something that is clearly not correct, which is a non-conservative force, for you to work. We're going to come to that discussion, and hopefully you guys see that. Again, this is in the same realm as I was telling you earlier, and how physicists think, because you need to be empowered with that thinking to be able to solve problems. Because if you Google right now, and we did not take Kirchhoff's rules at all, if you Google Kirchhoff's rules, you're going to get to a Wikipedia page that explains a lot of things and maybe gives you examples on how to use them, including when there is an inductor in the circuit, including when there is nonlinear electronics in it, when you have stuff that is, but trying to understand what are the justification for using it, that is the key. That is what hopefully we will get from this class, okay? So this is coming down the road, so it's not today. Don't panic and think that we're going to be doing circuits today, but we're going to be doing circuits in this class. Introduction to circuits, at least, okay? Okay, so let's think of that sense. Okay, so we found this force, basically the electrostatic force, QE. And this is how we define the electric field, as a matter of fact, okay? So if there is an electric field somewhere in here in space, and I bring charge Q in here, it's going to be subject to, if the electric field is in here, so this charge is going to be subject to a force that is parallel to that electric field and equal to the product of the charge times the electric field, okay? So that is easy enough to think about it this way. So what I'm going to do now is I'm going to have an electric charge Q by itself, or Q1, call it Q1, minding its own business. So this charge Q1 will create electric fields everywhere in space, and we saw that one. Obviously, I wrote the Q. Always when I write Q in here, I mean by it positive. So if it's negative, the force is going to be opposite to E, and that's it, okay? So it's still the same. So this is an algebraic expression, so you have to pay attention to that detail. So in this point in particular, so this is a point P in space, there is an electric field E in here, okay? As a matter of fact, everywhere there is an electric field next to it. So there is an electric field in here, and there is an electric field in here, and there is an electric field in here, there is a tinier electric field in here and so on. My interest is this point per particular, okay? This point P in space around it, okay? At a distance R from this charge, okay? Of a unit or a vector R, if you want to call it that way. And I want to bring charge Q2 from infinity. So Q2 was sitting at infinity, far away from this charge. And I'm going to bring it through this path, basically. This charge Q2 is going to be subject to this force F, which is on it, equal to Q2 times E, where E is changing clearly. Okay? At this point, this force is going to point this way. So this is the force F, which is QE. The displacement, of course, is this way. So I'm moving this way. Okay, I'm coming from infinity. So the dr is in this position. Okay, so the dr is in this way. And I want to know how much work is required for me to assemble these two charges. Obviously, if you're all interested in work, work is just a dot product of these two vectors. So the work in here for a small displacement, delta W, is going to be just the force times displacement, which is delta R. And these two vectors are opposite to one another, of course, and they're equal to Q2 times E times delta R. Okay? E for this charge, if you guys remember, is equal to 1 over 4 pi epsilon naught times the charge Q divided by the distance squared times the R hat vector. Okay? So this is basically the electric field E. So delta R and R hat are in the same direction, so there is no problem with them. Now, if I choose to come on a different path, if I choose a different path altogether and come this way, as long as I am moving toward the charge, I have a delta R. If I am moving at an angle, I have actually a change in the angle. So this change in here is going to be proportional to delta theta times theta hat. But theta hat and R hat are perpendicular. So in this displacement, the lateral displacement, I will not incur any work whatsoever because of the fact that this is a dot product between the vector E, which is always radial. In this point, the vector E is radial, and the displacement is perpendicular to it. So there is no work if I'm going to go sideways on this. The only work that matters is when I'm going straight through to the charge, to this point P, closer from the charge. So that's why at the end, what matters is just the radial displacement, okay? dr. So when I'm summing this vector, this E is always radial, and delta R has the potential of becoming radial or azimuthal in the angular direction. As long as there is a component for it in the radial direction, this is going to work. If I take a vector R in space, this is a vector R. I can change it in one of two ways. I can add to it a delta R in magnitude. So this is its magnitude is R. So I can add to it a delta R in the R hat direction, or I can change its direction by an amount delta theta. So this is theta, by the way. So this is delta theta in such a way for small changes that the arc distance will be just the radius times delta theta. And this is in the theta hat direction. The actual displacement of the vector is the sum of these two vectors, these two small displacement. So delta R, or dr to be more specific, can be written as, this amount is dr now, dr in the radial direction plus a change in the angular direction, r d theta, times theta hat, okay? So that is the potential to give me, that is not the potential, I mean, that is, I have two ways of moving around to get to my point. Either come straight through the radial direction or have displacement on a zigzag pattern away from it, basically sideways. But then ultimately I have to come through the radial. The radius has to change at some point, okay? If I want to really get to the point P. My point in here, since E itself is radial, this displacement doesn't matter because if I do E dotted with dr The only component that is going to be left at the end is E times dr, because R times hat times R hat is 1, and R hat times theta hat is 0 because they are perpendicular to one another, because cosine of 90 degrees is 1. Because of that, that is basically the reason why this integration can be done at the end. The summation for the work is going to be done over just the radial direction. You're asking, hey, this looks like it's a plane motion only because you took only one angle, but in space I can go this angle and that angle. There are two angles. In either case, both angles are perpendicular to the radial direction. So in polar coordinates in 3D, you have actually two angles. You have the one on the plane X, which is on the XY plane, which is the phi angle, and you have the theta angle, which is actually the, what is it called? The inclination. That is actually that's still also in this direction. So if you are on a basketball, okay, you can move one side to the basketball or the other. In other case, you're moving at an angle. But if you go inside, that is the radial displacement, okay? That is the only one that matters because the electric field is only radial. So when you do the dot product of the radial vector with the displacement, the only thing that matters is the displacement in the radial direction. Does this make sense so far? With this business of radial displacement of the electric field, which way is pointing and things like that. Because I'm about to do a dot product in here to find this work. Good. This is what I hate about this part of here, because a lot of this is abstract at this point. Yes. So far? Okay, at least one person is okay with it. So then the work dW is going to be E times dr. Basically, that's the point of the whole discussion. So if you have an azimuthal displacement along the angles, that is not going to contribute to anything because the dot product r hat is the only one that's going to survive this operation. So at the end, the work that is required in this case is 1 over 4 pi epsilon naught times q times dr over r squared. That's it. That's the work that is required for bringing this charge, a distance dr only. So, but bringing it from infinity to this point requires this amount of work. I'm sorry. This is just the electric field. I need to multiply it by Q2. I forgot to multiply this expression by Q2 now, because we're bringing Q2, and this one, I think we called it Q1. So the electric field is produced by the charge Q1, so I need to put my Q's back in here, okay? Because this is energy, so it's going to be in joules now. So if I do the integration now, W is clearly going to be Q1 times Q2 over 4 pi epsilon naught, the integral from infinity down to R, because we're coming to a point R in space, of dr over r squared. And what is the integral of 1 over r squared? Or 1 over x squared? Isn't that minus 1 over x minus Q1, Q2, 4 pi epsilon naught times 1 over r evaluated between infinity and r, okay? Yes? Makes sense? Or did I make a mistake with the sign now? So what that sign means is that I really need to do some work for me to do that. Because it's clearly this work is, oh, I'm sorry, there is another sign. Oh, I'm sorry. That's why I made a mistake. This sign is negative because of the fact that, yes, R is actually getting smaller. It's coming toward this direction and the force in the opposite direction. So I know I made a mistake somewhere with the sign. That's why I was kind of hesitant. So this dot product has a negative sign in it because of the force pointing in one way and the displacement in the other way. So this is basically why I have in here, I have to have a positive sign. Did I fix sign or are you guys following me or not? Because the integration of r, 1 over r squared is negative 1 over r, but I have a negative from the fact that the force and the displacement are 180 degrees with one another. Okay, very good. So now the work is, so there was a negative sign in here, and that negative sign fixes everything now. So clearly, when R is going to be 1 over R. When R goes to infinity, this is 0, because we assume that the potential was 0 at infinity, that there is no interaction at the infinity. And the work in this case is simply going to be Q1 times Q2 over 4 pi epsilon naught times 1 over R. So this is the energy now that is that we have actually stored now in these charges. Because if I fix now the charge Q2 in here, I have this much energy in here in the system. And this energy is exactly Q1 times Q2 divided by 4 pi epsilon naught divided by R. So this is an energy, okay? So this is basically in joules. The unit for it is still in joules. Okay. Now here is the challenge. We're going to bring a third charge in the mix. So if we bring a third charge in the mix, we're going to bring it to a different point in here in space. Of course, we cannot put it on the same place in here, otherwise we'll have a problem. So if we bring another charge in here, and we find the electric field due to this charge, and we find the electric field due to this charge, and we have to fight them. Of course, now we have to be very careful in here. We're coming whichever way. We're going to involve the dot product at the end. And we're going to do it using superposition, basically. We're going to ignore this force in here, this charge in here, and come from infinity, whichever direction we're coming at the end. What matters is just that dot product. So it doesn't matter the direction of E and dr. At the end, what is going to be left with is just that integration. So we're going to get that value. And now the second part in here, we're going to ignore this charge and do the same thing for the second charge and bring it from infinity. So it doesn't have to be the same direction. It could have come from any direction, as a matter of fact. As long as I'm coming in here, the only thing that matters at the end is this dot product that is going to be the radial displacement. And at the end, I'm going to build that much energy. So now if I have, and that's by superposition, by the way. So the work in this case, which is the energy stored now in the system, because if I release these charges, because I have to hold them in place, okay? I have to hold them in place. Because if I release one of them, it's going to fly away because of this repulsive force. So this is the amount of energy stored in the system too. So the amount of energy in this case is going to be the sum over all of the i's and j's of qi, qj, divided by 4 pi epsilon naught times the distance between the i's and the j's, okay? And first of all, I cannot be equal to j, but I have to be very careful in this summation, because if I do it straight out, I am double counting, okay? Because if I do the charge 1 and charge 2 and charge 3, for example, and I do this energy between 1 and 2, the energy between 1 and 3, and the energy between 2 and 3, I'm not done. I can do also the energy between 2 and 1, and the energy between 2 and 3. And if I go in here, I'm doing the energy between 2 and 1, and the energy. So I'm doubling the counting if I do really the summation. That's why I have to use a factor in half in here, so that this summation doesn't calculate the energy twice, okay? Because it's calculating it in here twice. So this is an energy of an assembly of point charges. Let me reiterate. I don't think that I made that point clearly as it should be. Okay, let's start again. Okay, so I have charge 1, 2, and 3. Charge 1, 2, and 3. The summation assumes the following. So I'm going to find the interaction of 1 and 2, and then 1 and 3, making sure that 1 is not counted in here by itself. Then when I go to 2, I'm going to count its interactions with 1 and its interactions with 3. Okay. When I go to 3, I count its interactions with 1 and I count its interactions with 2. So that is basically what the summation is saying. Start with 1, I equals to 1, and then sum through all of the j's. So I start with 1 and then do the interaction with the j's that are not equal to I, that are not equal to 1. So I do the interaction with 2, and then I do the interaction with 1. So that gives me the first step, which was this one, okay? Then I changed I and make I equals to 2 now. So basically, if I follow this prescription, I only have 3 charges. So I say sum from I equals to 1 and j equals to 1 to when I is equal to 3 and j is equal to 3, making sure that I cannot be equal to j. So what I do this sum in here, I will find q1 times q2 over 4 pi epsilon naught times the distance between 1 and 2. That's 1. Because I changed 2 now, I'm doing j, and I cannot put j equals to 1 because I'm doing 1. I have to do 2. Now plus q1 over 4 pi epsilon naught times q3. Because I have to end the j at 3, I'm done with the case of I equals to 1. Now I'm going to move to the case of I equals to 2. So this is I equals to 1. The case of I equals to 2, then I'm going to say, okay, I is equal to 2. So Q, 2 now, because I have 3 charges, Q2. I cannot do the, I'm going to start with J now. J starts from 1, so I'm going to do Q1 divided by 4 pi. This distance is between R and 3, by the way. 4 pi epsilon naught, the distance between 1 and 2, okay? Plus, the next term cannot be 2 because that will be a repetition of 2. I is 2 and j is 2. That's not going to work. So I have to do the next step, which is j equals to 3. So it's going to be q2 and q3 over 4 pi epsilon naught, the distance between 2 and 3. You already see this term repeating itself from this process. So now I is equal to 3 now. That will solve the problem. So we went from I equals to 1 to 2 to 3. And the same time, we're changing j independently from 1 to 3, but making sure j cannot be equal to I. So I is equal to 3. That means q3, and then I can start with j equals to 1 divided by the distance, 4 pi epsilon naught, the distance between 1 and 3, plus, now since I is equal to 3, and q has and j is equal to 1, now I can go to j equals to 2, which is q3, q2 divided by 4 pi epsilon naught times the distance between 2 and 3, okay? Let's see how many terms we have that seem to be repeating. These two terms are identical, okay? This term, 1 and 3 and 1 and 3 are also the same. Finally, these two terms, 2 and 3 and 3 and 2 are the same. So if I do this summation, I'm doubling the energies. And I only have one energy between every two charges. So I have to divide by a factor of 2 to get rid of this double counting. That's why there is a 1/2 in there. You guys see the utility of the 1/2 in this expression, in this general expression? So we need a 1/2 in there. Without it, it doesn't make sense, okay? So this is the energy of assembling a bunch of charges, okay? If it's an integral, we're going to sum through all of this double sums, basically, through the different charges, okay? As long as that distance does not overlap, otherwise we have a problem. So this is basically how much energy is stored in assembly of charges, and you need the factor 1/2, because if you don't do it, you're going to be double counting. And I did the example in here for 3 charges only, and you saw that we will end up with 6 terms, whereas only there are 3 terms only, okay? This interaction. Okay. Let's go back into physics 4a. Again, I just made the case for it, and argue that a conservative force from physics 4a will have a potential in such a way that this potential is defined by, in 1D, a minus du over dx, where u is the potential energy. If it is actually in 2D, you have to be careful now. This force can have, in 2D, this force can have an x component, which is minus the derivative of the potential with respect to x. But I have to do the partials now because this u can be a function of both x and y. Have you guys encountered the symbol partial already in your classes? Did you guys encounter this symbol or not? Which is not the regular D.
Didn't encounter it, but the professor just kind of very vaguely explained it.
Okay. It's really, I know when you guys do it in calculus, okay, at least some people, they did, some others, they did not. Let me give you basically a big picture also in here for it, okay? If a function, let's say, for example, sine of x, and I want to find its derivative, all I have to do is just use the rules of algebra to say this function, for example, f, its derivative with respect to x is, what is it, cosine of x, correct? Good. That should be it, isn't it? Okay, let's say, for example, the function does depend on actually two variables, y sine of x, and I want to take its derivative. This function depends on two variables, okay? So it depends clearly on y and x. I can vary y independently, and this function is a linear function with respect to y. It's clearly a line. So if this is y and this is the function f, this is the function that I can draw. Its slope actually is sine of x. So the sine of x is the slope of this function. That's just like a number, x12. So if you change x in this case, the slope will change for this. So it's like a parameter in this case, okay? But if I'm interested in the behavior of this function with respect to x, then this function is clearly a sine wave function, okay? Where y, in this case, is just the amplitude of this function. It's how big it's going to go up and down, that's all. So if you change y, you make it a much bigger function than if you do it in here. Same thing, if you put x equal to 0, this function actually is 0. Same thing in this case because they're of the simple dependence. So if we're going to take a derivative in here, I have to be very, very specific in here. What kind of derivative you're talking about? If you guys remember, the derivative is by definition, the value of the function at a later value. In this case, it depends on two variables, divided by the change in that variable. So this is what the derivative is, isn't it? You guys remember this stuff from your calc class or not? When delta x goes to 0. Yes, okay. So we're going to calculate this derivative now with respect to x. So what we're going to see in here is this is the limit when delta x goes to 0 of sine times, of course, this function is y, times sine of x plus delta x minus y times sine of x divided by delta x. Obviously, y has no business in here with this limit, so it can come out of the limit at all. It has no business in here, so we're going to take it out. So we'll be left with y, the limit of this function when delta x goes to 0, of sine of x plus delta x minus sine of x. Obviously, this is a problem because if delta x goes to 0, delta x goes to 0, but this guy also goes to 0. So we have to do something in here, okay, to find this thing in here. And there are several ways. First of all, you could use a trig identity, sine cosine, which is sine of x, cosine of delta x, plus cosine of x, sine of delta x, minus sine of x. So this is basically what this whole expression is. So I use the sine of a plus b rule, which is sine of a cosine of b plus cosine of a sine of b. This is a trig identity. So if I use that, and delta x is so small, okay, that its cosine is roughly 1, which means that I have sine of x and sine of x, they cancel, that's good. But then I have sine of delta x, it's so small that it's almost equal to delta x, okay? So at the end, this limit becomes y equals to the limit when delta x goes to 0. I'm going to the basics, okay? I know how to take the derivative of sine, because if somebody asks in here what is the derivative of sine, it's going to be cosine. But the point in here, I'm just going to the basic definition of what the derivative is. So at the end, it's going to be what? Cosine of x times delta x over delta x. So when the delta x is canceled, now take the limit, and the limit is going to be 1 times cosine of x, which is exactly what we need, y cosine of x. So this way, the way I define this derivative is specific to varying only x and keeping y constant. So for that, we use the symbol partial. Partial meaning that I'm taking a derivative with the specific variable in here, which is x, and not doing it with respect to the other one. Okay? I'm doing it with only one derivative. I have to be explicit in here and tell you which one I'm doing, which is a sine of x. I could have done the definition in the same token in there and say the limit of this function, delta y, minus f of y, f of x and y, when delta y goes to 0. So now it's a clearly different operation because x doesn't change. The y is the one that changes. So if I go back to my definition of this function, so it's clearly equal to, this expression is equal to y plus delta y times sine of x minus y times sine of x. And the whole thing is divided by delta y, and I'm supposed to take the limit of this expression when delta y goes to 0. Okay. Well, I have this y times sine of x and y times sine of x, they cancel, and I'm left with delta y times sine of x, and that is simply equal to delta y sine of x divided by delta y, the limit of this expression when delta y goes to 0. Again, cancel the delta y, and now take your limit as you wish, and it is clearly sine of x. So this is, again, I varied y, and I kept, in this case, x fixed, because they are independent variables. That's why I can do that operation. So in this case, the partial with respect to y of this function, remember, is written this way. What that says, what this partial presenting in this case is, take the derivative, change y, keep x fixed, and evaluate this expression. So that is basically what we're supposed to do. In this example, x sine of x, y sine of x, this is a function that clearly depends on two variables, x and y, and the derivative in here simply of this function with respect to x, ignore y, keep it constant, and take the derivative of the sine, which is a cosine. So it's y cosine of x. And the derivative of this function with respect to y is simply ignore the dependence of this function with respect to x and just find its derivative with respect to y, which is 1. Because this is a constant now, so it's going to come out sine of x. As a discussion point in here, I want you guys to do this function, okay? And you can think of any function you like. X squared e to the power xy, okay? I want you to find d with respect to x of this function. This is a function that depends on x and y. And I want you to also find d with respect to y, okay? So this should not be hard, okay? So we want to find df with respect to x and df with respect to y. So don't forget that you have a product of two functions in here. So it's going to be 2x squared times the exponential of xy plus y times x squared the exponential of x of y, xy, and you do the calculation. For the derivative with respect to y, there is only one y dependence, so you drop an x in here, so it's going to be x cubed exponential of xy. You guys know how to do this operation? Can you guys see that it's doable? Should be straight following the rules of derivation in this case with the, okay, oops. So let's do that, okay, since it's, so again, in this case, what I'm saying in here, take the derivative with respect to x of this product of two functions. So the first one is just 2x times exponential of xy. The second one is the derivative of this function with respect to x, which drops me a y and leaves the exponential. So it's going to be x squared times y exponential of xy. So this function is equal to 2x plus yx squared times exponential xy. Make sense? Okay. This one with respect to y is easy now because I only have y in the exponential in here. So this is constant, so we don't care for it. So it's going to be stay x squared, the partial with respect to y, because there is no y dependence in here, of e to the power xy. For that, I'm going to drop an x in here because I'm taking derivative with respect to y. So it's going to be x cubed exponential xy. Make sense? Okay, so here is another thing I want you to do now. I want you to do the mixed derivatives. I want you to take the derivative with respect to x of the derivative with respect to y. Take this derivative with respect to x. So take this value and plug it in here. Okay, now that's step one. So this is the mixed second, or they are second, okay, because it's going to be the reason why we need this is because down the road, we're going to introduce the gradient. I mean, the divergence, and the divergence includes the mixed derivatives, okay? So a gradient will involve only the first derivatives. And also, take the derivative with respect to y, whether of the derivative with respect to x, okay, of the function f. So take this result that we found in here and plug it in here, in the second one, and you should be able to find the second mixed derivative, and you should discover that they are equal, that this is equal to that. The mixed derivative doesn't depend on the order with which you do the derivatives because they are independent variables anyway. So in this case, it doesn't matter which order you take if you're doing the second derivatives, okay? So this is not really teaching you about partial derivatives, but to the extent we will need them in this class, okay? Because unfortunately, we are doing multivariable stuff in here, although we don't want to, but we will have some. And actually, problem 77 from this chapter. Now, problem 76 has a potential that depends on x and y and z. Okay, and you're supposed to find the components of the electric field, both in the x direction and the y direction and the z direction. Okay, so that is actually why we will need them for this thing in here. And you consider it as a bonus for you guys when you go to your calc class later on and do multivariables derivations and things like that. That is that. Now, here is a word of caution, okay? It sounds strange the first time you look at this partial derivative stuff. But this is really not as strange as it should be, because any function you see in real life is actually a multivariable function. The odd part of it, the odd thing actually that you really should be alarmed if you see it and you say, wait a minute, is this even possible? Is when a function that depends on a single variable and you see this symbol. If you see this symbol, or D whatever, that is actually an odd. That is where you're supposed to, wait a minute, is this even possible that the function depends on a single variable? In the lab, usually, we try to control the experiment in a sense, try to fix all of the other parameters and just leave one as an independent variable, and then study the dependent variable and how it changes with the independent variable. But that's a controlled situation. And even then, it might not be true that the function really depends on a single variable. So in real life, the temperature, for example, depends on the time, depends on the location, depends on the humidity outside, depends on all kinds of factors in here that are the insulation in your room. So it depends on so many variables, okay? So if you're going to plot that function of temperature, it's going to be a complicated function on several variables in here. And if you're trying to study the behavior of this temperature as a function of what? If you want to see how it changes with respect to what time? Temperature was this, something changed to something else. With respect to location, from this location to another location, it's different. With respect to humidity, probably is going to come into it. Pressure also comes into play. Insulation is going to be a problem. a heating source, for example, a joule heating, the lamp in there, all kinds of factors in there, so that they can impact that one in there. So this is really the odd thing. When you see something that depends only on a single variable and you're taught on how to handle it, it becomes kind of natural. So when you see another partial, you may be saying, wait a minute, it looks strange. That's actually the normal one, is the partial. This, what you thought is normal, is actually the odd one. Okay, it sounds like a commercial trying to sell you something. Infomercial. Yes. Did you buy it? Yes, no? Did you buy my arguments or not yet? Okay, seriously, okay, this is a very, I know it's probably you have never done this before. And there is always a starting point. So this is your starting point. So I gave you an example, and here we did already the first derivative. The second derivative is just basically taking the derivative of derivative. Since you already have a function, it looks a little bit longer, but that's it. But that you can do. Okay, so you're supposed to do it. And then, and that's it. That's for this part. Once you know how to do that, because we're going to find an expression for the force in 2D, which gives me an expression for the electric field in 2D. In 3D is going to be identical. All you need is just add another variable to it, okay? And we're going to find the potential for the point charge, and then potential for distribution of charges. Basically, we're going to make the case for it derives of a potential. And then we're going to be doing stuff with this potential, electrical potential, and how it depends on the charge and everything else, and its usefulness. Because if I can find the potential, then I can find the electric field. That is really how it works, okay? Are you guys going to do this example, hopefully? And you post it in the discussion? It's not, I really am relying on you that you do it, okay? If you have difficulty with it, please let me know so that we can work out the details. Sounds good? Okay, good. Look, we're going to be meeting in about 40 minutes, maybe. Okay. So we're going to do some problems and hopefully have some discussions. We may have to extend the lecture a little bit during that time, okay, just to get to the definition of the potential, the electrical potential. So we may borrow some time from the lab to do some lecture and then do some applications. So I see you guys in about 40 minutes, okay? I'm going to stop the recording.